All right, welcome in everybody to our quick test review for the first 9 weeks test in Precal this year. I'm just going to go through topics hitting some main points. After each topic, I would pause the video and go back through your notes themselves so that you can make sure that you've done some practice problems over these topics. For the 12 basic functions, some things we need to know about is the domain. Now, the domain of most all of the functions is going to be all real numbers from infinity to negative infinity to infinity, except for the square root function, the logarithm function, or the rational function. For the square root function, x has to be greater than or equal to 0, which means that my domain is bracket 0 to infinity, close parentheses. For the logarithm function, my domain has to be greater than 0, so the argument has to be greater than 0, which means that the domain goes from 0 to infinity exclusive. And for my rational function, the denominators cannot equal 0, which means that you would go from negative infinity to 0, pick up your pencil at a point of discontinuity, put your pencil back down after that vertical asymptote, and go from 0 to infinity. Speaking of vertical asymptotes, remember vertical asymptotes are always going to be x equals some number, and they occur because the denominator cannot equal 0. So whatever your denominator is, set it equal to 0 and solve, and x equal that number is the vertical line that is your asymptote for that graph. Horizontal asymptotes occur for graphs like the rational function. So horizontal asymptotes look something like these, okay, where this is a horizontal asymptote. Okay, it's a line horizontally the graph is going to get super close to and never touch. Another kind of graph that has a horizontal asymptote is your exponential function, but that one is always the same unless we translate that graph up and down. It's y equals 0. But for your rational function, the acronyms that you can use to remember what type of horizontal asymptote you have are BOBO, BOTN, and EATS DC. BOBO stands for bigger on bottom, which means that your asymptote is y equals 0. BOTN stands for bigger on top, and that you do not have any sort of horizontal asymptote, so like you would say none or not available. And EATS DC stands for exponents are the same. So the power in the numerator is the same as the power in the denominator. So you're going to divide the coefficients of that rational function so that y equals to the denominator on top, or the numerator's exponent divided by the denominator's exponent. You divide the coefficients. Last thing that we covered a lot in the 12 basic functions, but one of the definitions I wanted to go back over for you is boundedness. Remember, when a graph is bounded above, that means there's some maximum value for the entire graph, some y value that is higher than all the other points. Bounded below means that it looks something like this, where there is a y value that is less than all the other points. A straight up bounded graph means there is a highest and lowest point, like your constant function or your sine curves. Those are bounded above and below. And last but not least, you have an unbounded graph as well. Your cubic function is an example of an unbounded graph because there's no highest or lowest value for that function. Your end behavior is different. After we talked about the 12 basic functions this 9 weeks, gotta get used to saying that, we went over piecewise functions. So one of the main things that I noticed students getting stuck on is when we talked about the domain for piecewise functions, or the part of the piecewise function after you have the equation like f of x equal to, I'm just gonna make this up right now, x and x plus 3. It's this part right here, the given. So given x is less than 0 and given x is greater than or equal to 0. That part in green is the domain of the different parts of the piecewise function. Remember that this is referring to the x values where that part of the graph shows up, not the y values, the x values. So on the x values that are all less than 0, you would be following this rule, where the output is the same as the input. And anywhere further than 0, including 0, you're going to follow this rule, x plus 3. Another topic we covered this 9 weeks was operations on functions. We can add functions, subtract functions, multiply and divide functions, but the most common thing that we're going to do is to compose functions. So f of g of x, don't call that fog, oh my gosh, please do not call that fog. It's f of g of x is saying we're going to take the f of x function and we're going to plug the g of x function into it and evaluate the f function at the g function. Remember also that the carryover domain, or what we would call the carryover domain, comes from the inside function. So you got to make sure that the inside graphs, or in this case g of x, because it's f of g of x is inside, doesn't have any sort of restriction that we lose when we compose it with f, because that is a part of my final domain for the composed function. And last but not least, for this page at least, we covered inverse functions. A couple things I want you to remember is that a relation is a function if it passes the vertical line test. But a relation has an inverse that's a function if it passes the horizontal line test. So the relation becomes a function if it passes the vertical line test, and its inverse is a function if it passes the horizontal line test. Remember also that the range of the original function f of x becomes the domain of g of x, and by g of x, mark that out, we really mean the inverse of f. So the range of f becomes the domain of the inverse. So we've got to make sure that we check the domain of that beginning function so that it becomes the domain of my inverse function. The next topic we covered is transformations of graphs. So here's, again, all of the definitions that we went over. If we are adding or subtracting a value c inside the other function, we are doing a horizontal translation. Okay, so we're moving it side to side. Specifically, if we subtract numbers, we're moving the graph to the right. And if we add numbers inside that function, we're actually moving it to the left, horizontally. If we add or subtract numbers, value c's on the outside or behind, maybe in front of, but outside of the function, we're performing a vertical translation, where subtracting a number moves the graph down, and adding a number moves the graph up. Multiplying a number in front of the entire graph, so maybe distributing that inside, if that value is bigger than 1, so 2, 3, 4, 1.5, 3 over 2, as long as it is a value bigger than 1, this is going to be a horizontal stretch by a factor of that number c. And if the value I'm multiplying in front of the function is a true fraction, I'm using air quotes because that's not really a definition there, but if it's something between 0 and 1, like a half or a quarter or 0.8, then that's a vertical shrink or vertical compression by a factor of c, whatever number we're multiplying by. Now, if we're multiplying that number inside the function in the very front, and that value is bigger than 1, first of all, typo, this is a horizontal, and specifically a horizontal shrink by a factor of 1 over c, so you use the reciprocal. If that number is a true fraction, like 1/2, that's what you see inside, that's actually, again, a typo, horizontal stretch by, again, a factor of 1 over c, the reciprocal. Multiplying a -1 in front of the entire function makes a reflection over the x-axis. So you would have gone from, I'm just going to use the parent function for a quadratic, you would look something like that, and it would change to something like that, a reflection over the x-axis. And I kind of wrote that in the way of the other one, so let me write it up again. My bad. And if you multiply that negative number, -1, inside the function, this is actually a reflection over the y-axis. So just for kicks here, let's look at the function that looks like this. This is x = y squared, for those of you who care. If we reflect it over the y-axis, it's just going to flip around and end up looking something like that. So reflection over the x goes from a happy parabola to a sad, or something like that. And a reflection over the y flips it sideways. So those are my two reflections. If we know the transformations of graphs, we know these definitions and where all of these values will be added or subtracted, then we're absolutely fine to answer all of the questions about transformations that you might see on this exam. Live and learn those definitions. The next couple topics start to tap into polynomials. So we have a good amount of properties for polynomials that we need to go back over. The first is that the degree of a polynomial is the largest exponent. And the leading coefficient of a polynomial is the coefficient of the term with the largest exponent. So you're looking for what the highest exponent is, and then the coefficient of that particular term is the leading coefficient. And those two things, the degree and the leading coefficient, are all I need to be able to talk about end behavior of the polynomial. If you have an odd degreed function and the leading coefficient is positive, odd means opposite, positive means that we are going to be normal, like a normal y = x, or y = wow, I just lost my train of thought, x cubed, okay, the cubic function. That means the behavior is down to up. As x approaches -infinity on the left, my graph approaches -infinity. As graph approaches positive infinity, then my graph approaches positive infinity. For an odd degree polynomial with a leading coefficient that is negative or less than 0, odd is opposite, and a negative leading coefficient means my function is going to look something like that. So I have up on the left and down on the right. An even degreed polynomial, even goes the same direction, that has a leading coefficient that's positive. Think about your quadratic or any other even degree polynomial. It means that the end behavior is both going to positive infinity on the left and on the right. And an even degree polynomial with a leading coefficient that's less than 0 obviously kind of looks like this, which means both of my end behaviors are going towards -infinity or down. Multiplicity is how many times the 0 of a polynomial repeats. An even multiplicity, so 2, 4, 6, 8, on a particular 0 means that the graph does not cross the x-axis. I know I covered up those words, so I'll write them again. But at that point, it does not cross the x-axis. An odd multiplicity graph does cross the x-axis at that particular point. So odd means cross, even means bounce. It bounces off or does not cross. It'll touch it, but it does not bounce. And a few theorems to know. Remember that a polynomial function of degree n has a maximum of n minus 1 local extrema and a maximum of n zeros, which ties us into a fundamental theorem of algebra, which we will define on the next page. But that's a few theorems to know from our topic of polynomial properties, specifically polynomials of higher degree. We then started studying the zeros of a polynomial, both real and non-real. Probably one of the most important things to know how to do is to synthetically divide polynomials, so remember to set that up. You're just going to follow the steps, bring down, multiply, add, on and on. Setting it up, we have our value c on the outside and all of our coefficients listed in standard form. putting a 0 if it's missing anything. You bring down the first coefficient and then do multiply, add, multiply, add, multiply, add, multiply, add until you're ending up with your remainder, your constant, your x, and your x squared term listed in the bottom as your quotient. Now it might get bigger than that, so be ready to keep going with your powers, but that's generally speaking how synthetic division will work. Couple theorems to remember. The remainder theorem. It says that if a polynomial is divided by some factor, x minus c, then the remainder is the same as if we were to use f of c, meaning plug in that c value and see what the remainder is, because it should be what the value of the function is when you plug in c. Another theorem we need to remember is the factor theorem. It says for a polynomial function, x equal to c is a 0 of the function if and only if x minus c is a factor of the function. So this again relates our factors to our zeros. If I know a 0, I know a factor. Our rational zeros theorem is what we use to help simplify different problems when we don't know what zeros to start with, like when the problem hasn't told me what zeros to use or to try with synthetic division. And when we do that, all we're going to do is plus or minus p over q, make a list of those numbers, where p is a divisor of the constant term, so usually the last term, and q is a divisor of the leading coefficient, so the very first term usually, or the term with the highest power. Another definition, kind of a theorem, but more a definition, is complex conjugate zeros. If x is equal to a plus bi and it is a 0 of a polynomial, then we automatically know that a minus bi is also a 0. So imaginary solutions or complex solutions comes in pairs. You have to have both the first one and its conjugate as a 0. And therefore we get to our fundamental theorem of algebra, stating that a polynomial of degree n has n total zeros, some of those zeros may be imaginary, while some of them may be real. Remember also working backwards, let's say we don't start with the polynomial itself and are looking for the zeros, but if we're given the zeros of the function, we can multiply the factors together to write the polynomial in standard form. For those of you who liked the shortcut that I gave that day, the shortcut to multiply any binomial times any other binomial is to factor it so that it is x squared, sorry, not factor it, FOIL it, multiply it, double distribute. It'll be x squared minus the sum of those values times x plus the product. And that's especially helpful to use whenever we are using zeros that are complex conjugates of each other, because you can put those values into the calculator and not have to do some multiplication within multiplication problems. You can just use this shortcut. So you would take whatever c plus d is, that's your sum, and whatever c times d is, and that's your product. And if that shortcut is like, what? Does not make sense? Just double distribute the whole way. Last but not least, something else that we talked about in this class, this unit, is the intermediate value theorem. Okay, I have listed the intermediate value theorem here for you, so let's read it off together. It says, if f is a continuous function on a closed interval from a to b, and if f of a is not f of b, and k is any number between f of a and f of b, then there is at least one number c in the interval a to b such that f of c is equal to k. Super confusing theorem because it's mathematically stated, super simple concept. We need to show that number one, f is continuous on the given interval. So in this case, on the interval a to b. A lot of times it will just tell you it's continuous and that's enough. Other times you have to know that the particular type of function you're given is continuous all over the intervals. So it's continuous on that particular interval. We also need to show that f of a is equal to some number, so evaluate the function at a and evaluate the function at b and make sure that the numbers are not the same. and that value k that we want, we need it to be in between those numbers. So say that since k is in between those two numbers, that you have some value c between a and b that is equal to k due to the intermediate value theorem. So again, this is the first thing you need, that it's continuous. The second thing you need is that f of a and f of b have that number k in between them. So f of a is less than k, which is less than f of b. Therefore, a has some number c in between it and b, where f of c is equal to k. And that's the intermediate value theorem, and that's how you justify your answers. So I know it said this at each point, each paper here, but seriously, go back over the examples in your notes for the topics covered and make sure you understand most of them. If you have any questions whatsoever, now is the time to message your teacher on Remind, specifically me, and I will try to get back to you with a little bit of tutoring and a little bit of extra help. But you have all of these examples in the notes to go back over. You have also a bunch of videos on my YouTube channel, as well as a link to all of the notes in my handwriting in your Google Classroom. So utilize those to study these topics and be ready to take this test next time I see you. Enjoy your days off. I'm super jealous.